Hi, in this video, we want to take a look at multivariate normal distribution. Specifically, we're going to take a look at univariate normal distribution, that's one variable, and then we're going to look at bivariate normal. Okay, so a lot of times in stat classes, for some reason, we kind of go over univariate normal, then we just go over multivariate, and we don't really do an intermediate step of bivariate. I want to go over bivariate normal because I feel like it's really the most concrete representation of correlation between variables that we can really get because we have such a nice formula floating around for us. So I want to dig into that. I want us to take a serious look at it. Okay, so where we're going is that we're going to start considering multivariate normal. That is to say that we have normal distribution when we consider each dimension by itself, but we also have a higher dimensional ellipse for our density contours if we were to look at things from a higher dimension point of view. I feel like the only way to really get a feel for this for most people who don't have a lot of math background is to look at bivariate normal. I think it's the best way to start out. Okay, so for univariate normal, we're already familiar with this. We've dealt with this in Stat Methods 1, Introductory Statistics. We've got standard normal. So the density is 1 over the square root of 2 pi. Then we've got e to the power of negative z squared divided by 2. All right, so this is the classic bell curve centered on 0 and with variance 1. Z is any real number. The expected value is 0 and the variance is 1. We're familiar with this. We're comfortable with this. We know this already. Okay, well, if I want to just go with normal in general, what we can do a location scale transform on standard normal. So if we say that y is equal to sigma times z plus mu, u is a real number, sigma is positive, and correspondingly, this equation is equivalent to z equals this fraction, y minus mu divided by sigma. Then what we can do using basic calculus, if I take this density and I take this transformation, or this transformation, however you want to look at it, either way, then the density of y is going to be equal to g times the rescaling of z given y. Okay, so here it's going to be the derivative of z with respect to y in absolute value. Why do we do the absolute value? Because this is a density. Okay, so we do the absolute value of it. And when I do the derivative, I can see that the derivative here is just going to be 1 over sigma, because the derivative of z with respect to y. So for this part here, we're using this. All right, so this becomes 1 over sigma. Now here, z gets replaced by y minus mu over sigma. And then if I just go in, take this bad boy, plug it in for z up here, we get this, and we get the formula that we're very accustomed to. All right, so we know it's going to be 1 over square root 2 pi sigma, then e to the power of negative y minus mu squared divided by 2 sigma squared. All right, now here y can also be any real number. I didn't put it in the notes, but y can be any real number because z can be any real number. A location scale transform of any real number is, again, any real number. Easy peasy, lemon squeezy. Now, let's go on to bivariate normal. Now, what we're going to do here, we're going to assume that they are not independent, or they could be independent, but we're going to jump into the formula where we have x and y are marginally normal distributions. That means that if I take y given x or x given y, the resulting distributions will be univariate normal, but we're going to assume that they're not independent. Okay, so this is a much juicier formula, but this is really just an extension of what we've already looked at. Okay, so here, remember previously I had 1 over the square root of 2 pi. Well, now that I've got 2 variables, I've got the square root of 2 pi squared, which is 2 pi. Now, I've got 2 variables. I have an X and a Y. All right, so before I only had sigma, now I've got a sigma X and a sigma Y. All right, those both go in there. All right, now here's something that is new. We have the square root of 1 minus rho squared. Well, what is rho? Rho is the correlation between X and Y. Okay. So if you say so, all right. You know, just nod your head at it if you're not okay with it. Okay. So this rho is going to be the correlation, and it's going to be very important to this density as we progress. Now here, you'll notice I've got a whole bunch of stuff in my exponents. I've got a whole bunch of stuff in my exponent, and there's so much that this E notation of E and then superscript gets really crowded, gets difficult to put stuff in. So what I'm going to do, instead of putting E then a superscript, I put EXP to represent the superscript of the number E. So EXP is superscript E, in big parentheses. Okay, now let's keep on going with this. Well, it's going to be negative 1 over 2, which is very familiar to us. It's very similar to what we had previously in standard normal. But on the bottom, I'm going to have 1 minus rho squared. Okay, well, that's kind of interesting. Now here's where it gets really juicy. All right, now on the inside of this bracket, I'm going to have x minus mu sub x squared divided by sigma squared sub x. I'm going to have y minus mu sub y squared, sigma sub y squared. All right, so these look like parts of standard normal, or not standard normal, but normal, right? The rescaling, that's very natural to us. Here's the x part, the y part. Okay. And if I had just these two parts, didn't have this junk, I would have independent x and y, by the way. But we don't. When I look here, I've got this other stuff floating around. So I've got 2 times rho, parentheses x minus mu x, y minus mu y, and then I divide by the standard deviation of both of them. All right, so if we think about our stat theory course, if we think about it for a moment, and we think about the property of exponentials, if rho is equal to 0, this term would disappear. And if this term would disappear, then I would be able to factor this exponential. Remember, the exponentials, if addition, I can factor into 2 exponents into multiplication. All right, so if rho is 0, then this would just be a 1, so we won't care about it. This would disappear. And then I have addition in an exponent, which I can convert to multiplication. If I've got multiplication of densities, then I have independence. Okay, so the only time that bivariate normal has independence is if rho is equal to 0. That's something that's very nice about this. Now, I can also see if rho is close to 0, in that situation, it might take me a lot of data before I would be able to tell the difference between being independent and not being independent. I would need a rho value closer to plus or minus 1 if I have small data for it to be obvious that they are not independent. Kind of an interesting aspect. When we, so this is something to think about as if we were going to use this in modeling, down the road. And here, so when we look at this formula, some stuff to consider: x and y can be any real number. The mu's can be any real numbers. The sigmas have to be positive, and the rho is strictly between -1 and 1. All right, now we're saying strictly between -1 and 1, so it can't be -1, can't be 1. Why is that? Because if it was perfectly 1 or perfectly -1, then there would be a functional relationship between x and y instead of a statistical relationship between x and y. If I have perfect correlation, then really, from our point of view, we only have one random variable. And now measure theory kind of loosens that statement, but for us, we're not going to deal with probability theory too deeply. We're not going to deal with measure theory. We're just going to go, okay, that's good enough. We're not going to worry about almost always, almost surely type business. Okay, so if I was to go through and I was to generate data off of this, and so I generate a whole bunch of random variables based off of this, and I look at just the x I look at just x, just x, just x, and I drop the y's, I'll see that x will be normal with mu sub x as the mean and sigma sub x squared as the variance, and something similar for y. But, so here, if I looked at just this, I might think that I have independence, but I don't. All right, so let's consider the situation where I want to go through and I want to look at the distribution of y given x. Now, why am I choosing y given x instead of x given y? Well, because that's very natural for regression, and ultimately this is a linear models class. So what I want to do, I want to take this density and I want to convert this to the density for y when the x value is known. So here, what I'm going to do, I'm going to treat x as a constant, but y is going to be a random variable. I want to see what comes out when that happens. Well, if I look at this density for a little bit, I realize that all the x's and all the y's are in the exponents. Furthermore, they're inside the bracket in here. So if I want to work with this as a density of y, then what I want to do, I really just want to focus on what's in this bracket at first. I'm going to work on this part of it only. And what I want to do, I want to manipulate this into a format so that I can get the density of y by itself, and everything involving an x is kind of like factored out. And that's my goal. So what I want to do, I want to find the kernel of the density of y, treating x as a constant known value. All right, so I'm just going to focus on this bracket here. I'm not going to worry about any of the other stuff. I'm not going to worry about this -1 and 2 and 1 minus rho squared. I'm not going to worry about the exp. I'm not going to worry about this constant out front. All right, so I take a good hard look at this. All right, I see I've got something squared, the two things multiplied together, and something squared. Hopefully from college algebra, I go, hey, I've got a square going on, and I have a linear term for y. So remember, x is a constant when I look at y given x. X is a constant, so really I can look at this as a quadratic on y. I'm going to look at this as a quadratic on y. X is just a constant, it's just some number. I'm really not going to be too worried about it. Okay, so what I'm going to do, I'm going to rearrange my terms. I'm going to put all my y terms in front. So here I've got the y squared part. Here I've got y. And over here, I'm going to put down this. All right, so this part comes from here. This part comes from here. This part goes over there. All right, so this, and this are all part of the original equation. Now, what I'm going to do, I'm going to use completing the square. Now, my experience is that Americans suck at completing the square. I hate to say it, especially during an election year, but we suck at completing the square. It's just like people from other countries, it's just, they don't even look at it as a problem. They just do it. They don't blink at it. Americans just kind of like freeze up. So I'm just going to go ahead and do it for us because that's just how I roll. Okay, so remember, when I'm completing the square, I take the linear coefficient, divide by 2, and square it. Okay, so here I've got this y business going on. Here's my coefficient, -2 rho times the x fraction, -2 rho times the x fraction. Divide by 2 and square it. When I divide by 2, I get negative rho. When I square it, I'm going to get rho squared and then the x parentheses squared. And that is right here. Okay, so I've added something on. If I add something on, I have to subtract it off also because I don't want to get an imbalanced equation. So I take this, I divide this by 2 and square it, boom, I get that. Now, I'm going to take the same thing and subtract it off. So you'll notice I've got the same thing here. So why do I do that? Well, because if I have this and I have that, that's effectively adding 0. Does adding 0 change the equation? No, it doesn't. Okay, so now Why do we do this? Why are we suffering through college algebra? Good question. Check this out. I've got y minus mu over sigma y. So I've got the parenthesis. I've got the parenthesis and a row, and I'm squaring both of them. Now, what if I took what's inside the square, multiplied them, and then multiplied by 2? Well, if you think about your squaring formula back from college algebra, you'll know that this whole thing is actually a squared term. And since it's a square term, I can factor it easy peasy lemon squeezy. Now this junk, I'm just going to leave it alone. Why? Because when we're doing statistics, this is not, so this x stuff is not for us a random variable because we're considering it x as a constant. So this is just going to be a constant value that is multiplying the density to make it integrate out to 1. Okay, so I want to focus here. Well, if I think about this for a bit, and I use the regular factoring formulas from college algebra, I can see that this part is actually this squared term. Let's look at that. So I get the y fraction minus rho times the x fraction. And all of that is squared. Well, that's interesting. Now, if you think about univariate normal for a moment, it's always the random variable minus the population mean, right? So if I think about univariate normal, if I scroll back up here, when I look at this, I have the variable minus its mean, and then down here, I divide by 2 and its variance, right? Okay, so what I want to do at this point, I've got a square going, right? I've got a square going, so I'm close to what I want. I want to figure it out. I want to manipulate that so that I have y minus its mean, and I divide by 2 times the variance. Once I have it in that format, because of the properties of the normal distribution, I know that I have the right density. All right, so something I need to say. If I have an exponential and my variable has like a square in it and there isn't anything else like floating around, if I can somehow express it as a square, I know that it is a normal distribution. And that comes from your Stat Theory 1 class. Oh, by the way, if you take the actuary exam, bivariate normal is part of it. It was on my actuary exam, exam P. So this is one of the reasons why I want to go over this, is that if you do take the exam, you'll be better prepared for it. There was only one question though, but I mean, there's a lot of material that you have to be proficient at. Okay, so I want to focus in on this right now. What I want to do, I want to get this into a format similar to that univariate normal. I want to have y minus its mean divided by 2 times its variance. So I see that I've got this whole fraction business going on, so I'm gonna have to combine fractions. Once again, Americans hate combining fractions, but we're gonna do it anyway. You can tell that I'm kind of bitter from teaching college algebra year after year after year. All right, so, and I'm just doing the whole fraction business, just kind of plugging and chugging, working through it. And I'm just kind of just toughing my way through it. And eventually, I get to the point where I factor out a sigma y squared from all of this business. Okay, so now things are looking good, because at this point, I can see, remember, I subtract off the mean inside that square when I look at the univariate. So if I go ahead and factor out the negative sign, I see that I've got y minus all of this business going on. All right, so this tells me that the mean of y, when x is treated as a constant, is going to be x minus its mean times the ratio of standard deviations times rho plus the expected value of y marginally. That's kind of interesting. Okay, so now let's go ahead and slap this into the entire exponent. So remember, there was if we look back at bivariate normal, I didn't consider the fraction that had 1 over 2 times 1 minus rho squared. So let's go ahead and slap that on. All right, so when I go through, also by the way, I factor the x fraction squared to get here, which is not really a big deal for us because it's constant. We don't really care. All right, so we get 1 minus 2, then 1 minus rho squared, and then the standard deviation of y squared. Okay, so now I can see that, well, here I'm subtracting off a constant, right? Well, if I'm subtracting off a constant and it's inside an exponential, that means that it's multiplying by a constant effectively. So this part is going to be constant with respect to y. I can actually factor that out of the density by the property of exponentials. So I know that the density of y given x is proportional to this here. Okay, at this point we can stop because if I have a constant, if I know I have a density, theoretically I know I have a density, so I know it's going to integrate out to 1. So when I look at this, here I've got the mean, down here I've got the variance. Okay, so when I pull this all apart, I can see that the density of y given x is going to be a normal distribution. The expected value is going to be the ratio of the standard deviations times rho times the deviation of x from its mean plus the mean of y, and then the variance depends on, or the variance is equal to 1 minus rho squared times sigma sub y squared. Okay, so there's some things to pull out from this. Well, what happens when rho is close to 1 or negative 1? We can see that we're going to get a bigger slope off of it. What if rho is close to 0? Well, then there's not going to be any, x isn't going to have any influence at all, which is kind of interesting. What about the variance? If I take the variance to be plus or minus 1, I can see that y is no longer a random variable because it has variance 0. And when I say no, okay, so it can be a random variable, almost surely type business, measure 0, business, measure 1, whatever. But I can see that I can get maximum variance when rho is equal to 0. Okay, well, that's like the college algebra calculus way of approaching it. Now, let's go ahead and let's work with this in terms of matrices. So what I want to do now, I want to introduce matrix notation for this because in the next session, what we're going to do, we're going to be working in higher dimensions. And I kind of want this to be like a baby's first steps business. All right, so we're going to look at bivariate normal, but this time we're going to use vectors and matrices. All right, so we're going to take a mean vector, just like we talked about previously. We're going to take a covariance matrix where we have the variance on the diagonal, covariance on the off diagonal. I only have 2 variables, x and y, therefore it's a 2 by 2 matrix. And just to make things a little bit easier on the notation, I'm going to go ahead and say that z is our random vector. And we'll say that rho is between -1 and 1 strictly. And so that way we don't get any of the degenerate cases. We don't have to worry about linear dependence or anything like that. All right. When I do that, what it's going to work out being is that we're going to have this formula here. This is actually the multivariate normal distribution density. And this works for a number of dimensions as long as it's multivariate normal. Well, for us, well, okay, so what I want us to look at, we know that it's going to be the square root of the determinant of sigma, and we're going to have the square root of 2 pi squared. Now, this 2 corresponds to the number of variables we have. Now, this 1/2 will always be, this is part of it. And here, you'll notice that we've got z minus its mean transpose times the inverse of sigma times sigma minus mu. And so This should be familiar from previous sessions. And then we're dividing by 2. All right, if we go through and we start plugging, chugging, and working through this, we can see that this is going to be 2 pi on the bottom, the square root of 1 minus rho squared, and then we've got the variance of x and y, and this part stays the same. And if I keep on going, I can make this a little bit simpler by pulling out the variance from the square root, so that's standard deviation, and this will stay the same. So remember that when we are dealing with covariance matrices, they're going to be positive definites. Now, that's only, for this, it's only if rho is strictly between -1 and 1. If they're linearly dependent, then it's going to be positive, semi-positive definite. But we're excluding that degenerate case to make our lives a little bit easier. All right, so here, what this is basically saying is that this is going to behave nicely as a density, because this negative sign is going to make it negative, which means the exponential isn't going to get too big on us no matter what we do. All right, that's all I've got for you. Take care and goodbye.